Welcome everybody, infrared spectroscopy part 2 for the introduction. Okay, we talked about how molecules behave differently in different types of electromagnetic radiation. We're talking specifically about infrared and what the molecule does. We saw it has different vibrational modes and the energy changes when it does some vibration. Mainly two kinds. One is stretching vibration. We have a stretching of bonds and bending. So these are the stretching modes and these are the bending modes. These are pictures. Let's try to see what happens inside the molecule when it drinks up that infrared vibration and starts vibrating. All right, so it's bouncing around. You think molecules are these static things. They're always constantly in a 24/7 fitness room. They're dancing. They're just happy to be alive. Let's look at what they do when they absorb a lot of energy. The stretching mode requires a lot more than bending. So when they have a lot of energy, they actually change their bond lengths. So there are two modes of stretching vibrations: symmetric, where they actually go up in the same direction. Okay, that's symmetric. Or asymmetric. So this is the symmetric mode over here. Okay, or asymmetric, where you're going one up, one down. That's asymmetric. Okay, they don't break any bonds, but one goes up and the other goes down. Okay, so basically the bond angle doesn't change, but the bond length changes. Symmetric and asymmetric. All right, now there are bending modes as well. One of them is scissoring, where they come together like this, coming closer. Let's say this is a carbon and two hydrogens, CH2. They can do wagging. Again, you don't change the bond length here, you change the bond angle here. On the stretching modes, you change the bond length, but not the bond angle. All right? Here's rocking. How do you rock? Like in a stadium. All right? Everybody hold their cell phone up and then they start rocking. That's rocking for you. All right? So there you go. And then twisting is when you twist. So basically molecules are just happy to be alive and they're dancing when they get hot in the infrared region. They're pretty hot here. Okay, and here's rocking. And here's wagging. And here's scissoring. Basically they're just dancing away. All right. Great. So let's look at some for the CH2 where they would absorb. So for all of this dancing, obviously they got to get some shots of infrared. Where are they getting it? Every single one has a exact different frequency for that particular vibration. Let's say this is water, for example. All right. Oxygen and two hydrogens. These guys should be a lot smaller, but you know, we can use our imagination here. Let's say this is water. How many different modes does it have? Does it have in all of them or just a few of them? It depends on how many atoms it has, and you can actually calculate this. So number of modes of vibration. Both these are considered vibratory modes. So you can have two types, stretching and bending. Stretching basically 2 and bending 4. For most part, that's what the molecules do. All right, so here you can take, let's say, water. You can calculate the number of modes of vibration by just looking at the number of atoms. And 3 in -6 will give you the number of modes of vibration. N is number of atoms, and if this is water, it's H2O. You see 3 of them is going to be having 3 atoms. Therefore, 3n minus 6 is going to be 3 times 3 minus 6. That's going to be 3. All right, 9 minus 6. So they'll have 3 modes. And what are they? You can see a small spectrum down here for oxygen. All right, you can see there are 3 peaks. And here's one. This one really has 2 kind of merged. If you look at the bottom, you can see there's a little bit of a indent there. The lower energy would be the bend. And then the higher energy vibrations are the stretching. So oxygen is going to do symmetric stretch, which is just going up and down here, or asymmetric stretch. One long, one short. Okay, and it's going to do one of the bending modes. Okay, so let's look at what it's going to have 3 of them, and the lower energy would be the bend, and the higher energy would be the stretch. Okay, when you have a 2 atoms attached like this, CH2, OH2, all of them would have symmetric and asymmetric. If you only had one, like a OH, or let's say an NH, that's just one bond, then you would have basically, just one mode of stretch. But when you have 2 like this, you would have symmetric and asymmetric stretch. All right, so that's going to be for water. So 2 stretch, 1 is asymmetric. Asymmetric needs a little bit more energy than symmetric, teeny bit more. And then 1 bending mode. And the most common one is a rocking mode. Okay, that's kind of a lower energy one. So even in the bending mode, scissoring typically is a little higher energy than wagging and rocking, and that's a little bit higher energy than twisting mode. For example, if you take CH2 and do the same thing, if you take CH and H, you can have stretch and bend. This is just an example. In the stretch, you can have again asymmetric and symmetric. The higher energy would be asymmetric, and the lower energy absorption would be for the symmetric stretch. And then you would have the bending mode. So for the bends, you can have again all of them. Basically, you'll see scissoring, and you would see rocking at the very end, and twist and wag. All right. So for the CH, on the infrared spectra, we're talking typically in the far infrared, you would have a absorption for the symmetric stretch at 2853. If you look at that for the asymmetric, it's 2926 centimeter minus 1. This is wave numbers. This is 1 over lambda. Not frequency, because frequency is C over lambda. This is 1 over lambda. But you can see when the frequency goes up, the wave number also would go up. For your scissoring vibrations for the CH, this is 1450, and you typically see a peak for that there. And the twist and wag are also around 1250, and the rock is around 720. All right, so here's a spectra that shows CH vibrations, okay, basically CH vibratory modes, and where it's absorbing. So over here you can see the one furthest to your right would be the asymmetric stretch, which is this one. This actually has CH3 and CH2, but this would be your CH2. Then you have your symmetric stretch. The asymmetric is going to be the higher energy absorption. So the molecule is basically drinking up energy for the asymmetric stretch in here. then the molecule is drinking up in the symmetric stretch in this region. Okay, and that's what you're seeing on the spectra, how much it's drinking, and the intensity shows how much. But what's really important is exactly the wave number here, okay, because that's very important, that wave number here is a constant for all CH bonds across the border. Whether it's from a long chain, short chain, polymer, it doesn't really matter, but it's always going to be absorbing in that region. So by looking at that, you can identify a CH bond. Now here's your scissoring vibration, 1450 around is where you're going to see a scissoring vibration. And then the rocking vibration here around 720 here. And you typically get something around 1350. Let me say this is a bend. Sometimes you only see some of them because they're not really intense enough, okay? Sometimes like a carbon-carbon bond, you won't be even able to see because it's kind of buried in here. Now, how do we know that we're not kind of imagining all of this and this is actually true? Well, we can do mathematical calculations to show that it's true. For example, take this bond, okay? So you can have a stretch here, this molecule. This is a spring, and you can treat the bond as a spring. So spring in and out, in and out. And see the stretch and expand, okay? It's contract and expand, just like a spring can do that. A bond can do that too. It's elastic. How do we know that this is all really true and we're not kind of making it all up or imagining stuff? We can actually calculate these values. So calculation of wave number, okay? So let's say we treat this as a spring. And we know from Hooke's law that the force is equal to the force constant, and that's very unique to every type of material, times the displacement, right? You've done this before in physics. So we can use the same force constant here to calculate our wave number. So our wave number here is 1 over 2 pi c, which is the speed of light, times square root of the same force constant k over a reduced mass or mu, which is basically m1 times m2 over m1 plus m2. Now the m1 and the m2 refer to the atomic masses of this molecule. So let's say this is carbon and this is hydrogen, this is 12 and this would be 1. All right, and the force constant would be, very unique to that bond. So all of this works out to be 4.12. The force constant, let's say we can calculate this for a CH bond. That is going to be 4.12 because these are all constant values, times the square root, and here this is 5 times 10 to the 5 dynes. It's a force over centimeter per centimeter divided by what you may call the reduced mass, which is 12 times 1 over 12 plus 1. Okay, and this all works out to be 32 centimeter minus 1. I mean, that's really close to, the experimental value. So this is theoretical or calculated value, and the experimental value is about, 2,900 or close to 3,000. So we can also go in and calculate these if we knew the force constants for these bonds, and which we know for all of the bonds. Now, as the bond strength gets more, your frequency is going to go more because this is going to be proportional to the bond strength. As the mass gets to be larger, then your wave numbers are going to get lower. Okay? For example, CH bonds are going to be in here, CC bonds are going to be in here because the mass is higher. CCl bonds are going to be in here because the mass is even higher. So as the mass gets to be higher, your wave numbers shifts this way. As your bonds get stronger, the wave numbers shift this way. That's a very important point when we talk about frequency of stretching and bending in molecules. All right. So in summary, I'd like to say that all molecules have vibratory modes that are stretching or bending. And we can calculate how many different stretching or bending modes they have by using this equation, 3n minus 6, where n is the number of atoms. Typically, asymmetric stretches are going to be a teeny bit higher than symmetric. The bends are going to be a lot less than the stretches. And in the bends, you can have 4 types. And you won't see all of them all of the time. You may see 1 of them or 2 of them. But typically stretches you would see, and they're very intense. That means they're absorbing a lot at that frequency. All right? So these are medium, these are strong. We can actually calculate and see that there is a correlation between the calculated value and the actual experimental value. In the calculated value, we're treating a bond like a spring. And so we have Hooke's law that tells us the force is equal to the force constant times the displacement of that bond. Okay, so here the delta x. So here we are using the same force constant here for molecules, and we can use this equation to calculate, and we can see that it really correlates very well to what we get on our IR spectra. So let's look at some more stretches and bends. See you soon.